Okay, so this morning we are very happy to have Professor Sumitas from Kentucky University to give us comments about target space entanglement.
Okay. So this will be a talk about a set of ideas which have been around for the last 4 or 5 years, and the idea is to try to, well, I'll tell you about the motivation of why we are doing this. So in way of introduction, so let me just mention the kind of entanglement we usually talk about in field theories. I'll call them base space entanglement. So you have a quantum field theory, it's defined on some region. You take a sub-region of that simplest sample. And if you are interested in observables which are restricted to only this sub-region, then there is a reduced density matrix, which I will write like this. So this object is the state of the entire system. So I shouldn't call this B, which is A plus B together. So this is the density matrix. For example, if you're starting with a pure state, this is a product of wave functions. And if I'm only interested in observables which are localized in this region, then in this state, I can write this in terms of a reduced density matrix. So that's quite standard. And of course, in relativistic quantum field theory, this object is divergent. We understand why it is divergent. It's divergent because of very short distance correlations which are across the boundary. And famously, in ground states, if I compute a thing like this, the entanglement entropy which associated with this density matrix becomes the area of the boundary surface times an appropriate power of the cutoff, where d is the number of space dimensions. Okay. Very good. In holographic theories, there is a beautiful geometric understanding of this, namely if the field theory is defined, say, on the boundary, then what you are supposed to do is to draw an extremal surface which is sort of anchored on the boundary of this A. And the Ruther-Kayanagi formula tells you that you want to calculate the entropy of that extremal surface, divide by 4 times the Newton constant, and what you will reproduce is a field theory entanglement entropy. This divergence is, of course, present there. It has got to do with the fact that near the boundary of ADS, there is a large region of space. It sort of appears as an IR divergence in the gravity description. This talk will be about notions of entanglement which do not involve a division of the base space degrees of freedom, but entanglement of internal degrees of freedom. So let me tell you a few words why one would be interested in this thing. Of course, the most common manifestation of gauge gravity duality is ADS-CFT. There is a CFT which has some base space, so you could talk about something like this. But of course, there are well-known holographic theories where the analog of the CFT is not something which is a quantum field theory, but something like quantum mechanics, for example. And this I'll talk a little more about. So this C=1 matrix model, whose a sector of that is dual to two-dimensional string theory, where this has a single matrix function of time. It's a quantum mechanics of this matrix, which captures the physics, at least some part of the physics of the 2D string theory. A slightly more powerful thing, but much less understood, is a BFSS model, where you have 9 such matrices, and it's supposed to be very, so it is, the model is just what is basically called D0 brane quantum mechanics. And its dual thing is, depending on the kind of limit you take, either the gravity in the background of this D0 brane quantum mechanics, or if you're a little more ambitious, is flat space M theory. So one of the things that the Ruta-Kayanagi formula tells you is that, you know, the larger the entanglement between A and B, the larger is this surface. So the larger it sort of goes into the bulk. So there is a connection between the region where you have a smooth geometry and the entanglement. Okay, I'm not talking about things connecting, but wormholes or anything. It's a very, I think, uncontroversial part. So you might wonder whether there is such a connection in these models where there is no base space, there's nothing to talk about, there's no quantum field theory, but there must be something which, if this is true, there ought to be something which captures something in the gravity description. Okay. I'll now give an argument that even in ADS-CFT, this is something one has to talk about. No, if there is something, it has to be the entanglement of this matrix degrees of freedom, and we want to make it more precise. I mean, the aim of this entire exercise is to make a notion of entanglement of these sort of internal degrees of freedom very precisely defined. Okay. So let me give you another argument that even in standard ADS-CFT, one needs to think about this. And this comes from the observation of Susskind and Witten, which in a sense captures the some essence of holography. So in their example, you take ADS 5 cross S5, you use some coordinates. I don't know what they are called. I think they're called bulk coordinate, ball coordinates. Whole square. So it is like a ball at a given time slice. R equal to 1 is the boundary, R equal to 0 is the center in this coordinates. And what they did was to calculate the area of a surface which is a little bit away from the boundary with some difference which is delta. So if you do this calculation, what you find is that the area of this in ADS5 cross S5 is given by this formula. There are 8 powers of R, which comes from the fact that there is an S5, which gives you 5 powers of R, and this is a SQ, S3, which has 3 powers of R. That's where it comes from. And what they said is, okay, so let me use this in the Bekenstein bound. The Bekenstein bound tells you that the entropy of anything within a big surface, the maximum possible entropy is the area divided by Newton constant. And if you put in everything, this object, let me call it A delta by Newton constant. It's like R to the 8, GS square, LS to the 8, delta cube. They use the standard relationship between these bulk quantities and the string theory coupling. GS is the Young-Mills square. This becomes n square by delta cube. And the argument is that what this means, that if I should think of delta as an UV cutoff of the field theory, and so it's like the field theory is living on the space with little cells of each delta size. The volume of such cell is delta cube because it's in 3 space dimensions. And it associates n square degrees of freedom with each such thing. It's of course consistent with everything we know about safety.
Entropy is a number of states,
Right.
and then there's the issue of degrees of freedom.
Yes.
I was always confused that they did not seem to distinguish these two in their paper, because you're in the vacuum state, there is actually no entropy, while A by 4 corresponds to an entropy and not a count of degrees of freedom, which is not an invariant notion. In some other choice of variables, the number of states is the same, but the degrees of freedom are not the same. So what exactly is the idea?
So I think it's the intuition comes from normal non-relativistic systems where the entropy saturates with the number of degrees of freedom. I think so. It's a extrapolation. It's a very wild extrapolation of that. Yeah. Emil has something.
Yeah, I think basically they were thinking along those lines that if you say, okay, this is the count of the degrees of freedom. Now, let me excite them.
Exactly.
Right. So, we can ask, what is the entropy of a black hole that has that radius?
Yes, that's another way of putting it. But I think Samir's question is that this is empty space, so there is no entropy really, but there is certain count of degrees of freedom.
But I think the intuition is that those degrees of freedom don't move somewhere else if you excite them to make a black hole.
Right.
So the degrees of freedom that were there in the vacuum are still there when you're making a black hole.
Yeah. Thanks for Okay. So this is okay, but then in another set of papers by, I think, Polchinski and then Susskind set, completely realizing that this is really a wild extrapolation, is to say that let's apply this to a region of ADS space which is of the side of RADS. Okay. If you work through the various formula, what this corresponds to, so a region of size RADS, that actually corresponds to delta very small. Delta equal to 1, in fact. It's order 1. I mean, you can just calculate what kind of area, what kind of volume would have the invariant size of RADS cube, and that's what it is. So if we apply this formula to that, which one probably shouldn't, but as a matter of order of magnitude, that's not too bad. Then you realize that this should contain n square degrees of freedom, because delta is 1. So that seems to suggest that if I'm looking at scales which are RADS or even smaller, the most important part of the degrees of freedom which are sort of roughly accounted for are these internal degrees of freedom. The fact that the field theory which is living on some space, so there is a spatial degrees of freedom which are, encapsulated by this, sort of becomes less important. And this is the problem of sub-ADS scale locality. I mean, why is physics local at scales which are much smaller, namely than the ADS scale, which we know it should be, because if open-closed duality is correct, it should be the string scale where physics should be local, has something to do with this internal degrees of freedom. So we need to understand, how sort of internal degrees of freedom get sort of metamorphosed into gravity degrees of freedom. Yeah.
If you have a small value for delta, then the n square over delta cubed.
No, so not small, order 1 value.
No, but in the earlier thing, when the delta was small,
yeah.
That is the number of ADS-sized patches around the boundary or all through the interior?
No, it's a number of UV cutoff size cells on the boundary.
On the boundary.
Right.
And UV cutoff is how much?
Delta.
So delta.
That is what is being, everything in ADS units.
Right.
Right.
So if delta is a pure number like 10 to the minus 3, then we are talking of a physical cutoff, which is ADS radius times 10 to the
this
minus
very
3,
small thing. Yeah.
but around the boundary.
That's right. Very good. We will see that trying to think about this will lead us to notions which are very precise in the kind of field theories which we are going to discuss, but which in some limit should reproduce a notion of entanglement in the bulk. Now, of course, in the theory of gravity, that's a very funny concept. So this has got to do with bulk entanglement. Because in the theory of gravity, where the metric is dynamical, you cannot just say that this is a region of space. It doesn't make any sense. Unless you're in some limit where, like a very semi-classical limit of small fluctuations of the metric, where you use that background to define what is a region, and you treat the dynamical gravity as like perturbative fluctuations. That's what people usually refer to when they say it's bulk entanglement. It's entanglement of these perturbative degrees of freedom, what one is considered. So what we would really like is to have a notion which has something to do with the bulk. I mean, we will be led to notions of entanglement in the bulk. I'll say in what way it is precise. It sort of reduces to that thing in some limit, but it is defined properly everywhere in all regimes. So we'll see what that got to do with it. The other thing which we'll find connected to this issue is notions of entanglement in string theory. That cutoff dependence, that divergence is a UV divergence. So very naively, you would think that string theory shouldn't have anything like this. I mean, if you're talking about low energy field theory, there is an argument due to Susskind and Uglum that that divergence is sort of absorbed into the Newton constant. But if you are doing string theory, there shouldn't be anything like this. String theory, anything you should calculate should be finite. Or in other words, this epsilon should be replaced by the string length. And you might want to try to figure out how to get this. Now, this has a very long history since the early 1990s, because, of course, it's very tricky of how to define such an object in string theory, but I think it's sort of pioneered by Dabolkar. There is an approach. It's not clear what that is. And the approach is that to take a replica manifold, the replica method of calculating entropy, and put the string on the replica manifold and try to calculate things. So that's a long program, which, as I said, has a long history. I don't think there is a very definitive conclusion yet. There's some recent works by Haldar and Jafferis, by Aaron Wall, Tadashi Takayanagi, all these things trying to make sense of this thing in string theory. So in fact, when this thing was first raised in the 1990s, so I thought that there is a string theory we sort of know a little bit about. That's two-dimensional string theory, which is up there. So why don't I try to make sense of this quantity in 2D string theory? Yeah.
For example, we have let's say n equal to 4 super young mu is UV finite. But
Any?
N equal to 4 super young mu is UV finite. Yeah.
Okay.
Non-perturbatively even well-defined.
Okay.
And suppose you consider entanglement entropy, and it's still UV divergent. It's just a property about the fact that you have infinite degree of freedom.
I think n equal to 4 young means certain things are finite.
Yeah.
But I don't think everything.
No, of course,
Yeah,
that's
yeah.
precisely what I say.
Yeah.
Yeah, entanglement entropy is still UV divergent. It's
That's right.
Well
That's
understood.
right.
I mean,
Yeah.
it's just a infinite number of
I
degree of
agree.
freedom.
It's a
Yeah.
possibility.
So why
it would
do
still
we-
be, yeah.
Why do we
It's a
say?
possi-
Why do we say in string theory that we have?
It's a-
to-
let
yeah.
me just go the kind of arguments people give. As I said, there's no proof. Okay. So one kind of argument is the following. I'm going to try to say why people believe that. Okay. What I will calculate is finite, period. I mean, there's no issue of that because that's a calculation. Okay. But so let me tell you why people believe that. One of the beliefs is the following. Suppose I take the entanglement of half space. This space is A and that is the complement B. So you break it up to a thing, infrared, regulate the whole thing. Now, this is well known that this object is nothing but the entropy which is associated with the Rindler horizon. Like if you just calculate what the density matrix is for this thing, this is nothing but the Rindler Hamiltonian. Okay. If you take Rindler space, so let me draw Tx squared. So I think there is an old argument, I think originally from 't Hooft, which said, well, what we should really do is you calculate, so the Rindler space in some Euclidean continuation, of course, just a disk. There's nothing there. So you take a little strip between rho and rho plus d rho, and you're supposed to calculate the standard thermodynamic entropy of this strip, and then integrate over all strips all the way to infinity. Okay. So let's take a massless scalar field. For a massless scalar field, the entropy goes as the temperature raised to the power, the number of dimensions. But what you should really use here is not the Rindler temperature, which is temperature at infinity, but the local temperature, which is appearing because of the redshift. And this local temperature, just 1 upon 2 pi rho. Okay. So the total entropy, so this is the entropy density, is basically an integral of this. And so that receives a large contribution from this cutoff surface here. So that goes as 1 upon epsilon raised to the power d minus 1. Okay. And that, of course, if you look at what is this little thin strip near the Rindler horizon, it's just precisely the region, which is very close to the entangling surface. Okay. And then the argument went, well, suppose I'm able to do this thing in string theory. Now, in string theory, famously has a Hagedorn transition. So the temperature, the entropy density would not go like this. There is a maximum temperature where things will be cut off, in some way. That's the string length. And therefore, if you're able to do a calculation like this, you'd get a finite answer. Okay. Now, again, this is not a proof. Neither this is a real calculation. So what I think Dabolkar and collaborators are trying to make this thing precise by trying to define string theory on this very non-compact orbifolds, doing a calculation. From what I understand by talking to him is that they don't have a really firm conclusion, but sort of indications that this thing is actually finite.
Just to clarify, suppose the temperature does saturate at some Hagedorn value,
Right.
but the number of degrees of freedom are actually rising. So it's not so clear that the entropy will actually become any smaller, right?
I see.
Because, right, you got to see what all the gravitons are doing. So if you broke up the string into all its fields, like the graviton and the string and so on, I know it's not exactly like that, but suppose you did that anyway, then you could look at it one by one, and the gravitons would just do exactly what they were doing.
Exactly. In fact,
And
in
the second
string,
mode was the massive particles would do something more. So somehow the modular invariance has to come in, blah, blah. But I'm just saying the Hagedorn temperature is not so clear because the degrees of freedom are going up.
In fact, in perturbative string theory, the entropy is precisely the sum of entropy of the modes. Even though, you evaluate it by a modular invariant partition function. Right. Yeah. So there must be some magic which is happening, people talk about phase transitions and, some magic of degrees of freedom changing near the Hagedorn transition, which, if at all, could be responsible for this. Yeah, that was my feeling, but that's what Atish says. That you could make sense of it. I don't know what it is. Okay, so I'll be a little more conservative and, not talk about this, but try to think of what can be a quantity which is relevant. And I'll start with these class of models like the single matrix quantum mechanics or the BFSS model. What kind of quantity could be there? Now, the main problem with trying to understand these things is that if these were just models of matrices, just some quantum mechanics of a matrix, for example, of a single matrix, it's some n by n matrix, I could have just said that I take an m by m block of it, and that would be my subsystem. Namely, I have a wave function, which is a function of, and the rest, a, b, right from 1 to m. And any kind of operators which you make out of these things, I'll start with the full wave function, integrate over the rest, obtain a reduced density matrix, and that reduced density matrix will give you this. But this is nonsense. And the reason why this is nonsense is because these theories are actually gauged theories of matrices. So there is a gauge invariance, which is a UN gauge invariance. You can fix that gauge invariance to a certain extent, but the effect of that is to move around this block. There's nothing sacrosanct. about having an M by M block sitting there. Okay. So we want to make sense of this in terms of gauge invariant, in terms of come to a definition which respects this gauge invariance. Yeah.
Yes, one could also think about just like having a background. You break it to a smaller subgroup, then still okay, right? To talk about this.
Yeah, you could do that. Suppose there's some breaking, but of course that's gauge invariant. I mean, you don't. I mean, it's in some particular gauge this might make sense. But there is a gauge choice there. I mean, just like in standard model, there is a unitary gauge in which the Higgs has a wave. But of course, the thing that acquires a wave is the gauge invariant quantity. Yeah. Yes, and we will come to that. Like under what situations this actually would make sense. Okay. But we'd like to start working from the very beginning with gauge invariant notions. Okay. So the gauge invariance means that I got to identify that this is a singlet where U is an n by n matrix. And there is a Gauss law which imposes the local gauge invariance on the states. So let's start thinking about a single matrix. If I have gauge quantum mechanics of a single matrix, the action would be something like this times some potential, where dt is whatever it is. And of course, in t's real time, in 0 plus 1 dimension, there's nothing there in AT. So you can always pick a gauge. It's just one of the gauge choice. AT equal to 0. But this comes with the Gauss law. The Gauss law basically states acting on the states is 0. This is the generator of remaining gauge transformations. This generates U independent of time. You suffix the gauge AT equal to 0, so whatever remains is the time-independent gauge transformations, but those have to be imposed on the physical states. Okay, otherwise it's not consistent. But what this only means is that psi is a singlet. In fact, you could add things to this source terms such that psi is some representation of the gauge group, but it's sort of fixed. So we want to look at wave functions which are singlet. And we can use that remaining gauge degree of freedom to diagonalize M. That's always possible. So M goes to eigenvalues. Now, this has been known for centuries that when you do this, when you go to eigenvalues, then there is a change of measure, a Jacobian, times a very famous factor which is called the van der Monde determinant. Now, the details of this are not going to be important in what we are talking. And it is convenient to think of wave functions which are, let me call this as wave function chi. Okay. Now, the original gauge symmetry has been fixed 2 times. And first you chose the gauge choice AT equal to 0. and then you diagonalize the matrix, but then you still have a gauge degree of freedom, which is interchanging the eigenvalues. So it's the Weil group. So chi of has to be so this is now the statement that this is gauge invariant. So symmetric wave functions. So sometimes it is, in fact, that's probably the best way of thinking about it, is to define a new wave function where you take like this, and then new wave function is antisymmetric. Okay, so this is standard many body physics now, except in one dimensions. You have n fermions which are moving on a line, and there's some external potential. The details of this Hamiltonian are not important from what I'm going to say. Okay, very good. So what do you do when you have n fermions in many body physics? So we have n fermions on a line. Here is this line, there's this fermions, which are moving under some external potential. These are, of course, fermions, so identical particles. So I can't say which particle is what, because they are identical. And this, of course, is exactly equivalent with the second quantization of this. So what does second quantization do? It introduces a field, which is I of x. I'm just using the Schrödinger picture. So this field, well, I don't know why it is called second quantization, because the same psi was used. I mean, I don't, whatever it is. I mean, this, and then, of course, for example, a single particle state of these fermions would be like psi dagger of x acting on the fog vacuum, and n particle state is automatically, if you take this to have anti-commutation relations, you can describe n particles. The thing I wanted to emphasize that this is no approximation, not a different, this is the exact rewriting of a many-body wave function in terms of second quantization. Okay. So I have a Hamiltonian for second quantization. I mean, the Hamiltonian is sort of looks like this, plus whatever, some potential, psi dagger psi, whatever you want to what. If you want interactions, add interactions. This is a standard field theory. The only thing is that it's not relativistic, because it has to be equivalent to a theory of n fermions. So this is non-relativistic field theory. So this is non-relativistic field theory. And in this non-relativistic field theory, the wave functional is a function of some Grassmann objects which are called psi of x. Those are the eigenvalues of the operator psi of x. Okay. So if you have a field theory like this, so you might think that we know how to talk about entanglement. You take a region here, call it A, the rest is B, this is B, and this is B. Forget about this fermions. Now we are doing field theory. So if I have observables which are made out of the fermion fields which are only in the region A, just like what we did in relativistic field theory, I should be able to define a reduced density matrix. Okay? And that density matrix sort of quantifies entanglement of a region A with the region B, not with a certain number of fermions with the rest. Okay. The reason why it doesn't refer to entanglement of say 10 fermions with the rest is because the wave function tells you that there's a certain probability of having some number of fermions here. Okay. So that number is not fixed. So very good. So that's what I had calculated long time ago using rather bad methods.
Sorry, Sumit, just want to make sure.
Yeah.
So in the original matrix model, you have the Wigner semicircle distribution of eigenvalue.
Right.
So is it what you are computing? Is it the
That's the Fermi surface.
Yeah, the fermionic representation of that ground state, and you want to compute the entanglement for that distribution.
So as I said, precisely what we're going to do, conceptually speaking, you have psi, some degrees of freedom like this. This is your original wave function, okay? And then you define a reduced density matrix. It's a Grassmann integral. This is what you want to compute. That's the reduced density matrix associated with the region.
So physically, this wave function represents the semicircle representation of this eigenvalue.
No. Semicircle representation, or whatever it is in this, that depends on the potential. I mean, for the potential, it could be a hyperbola, the Fermi surface. That representation is the support of the density of eigenvalues. Okay? The ground state. Whatever, if you want an excited state, take an excited state. If the ground state is what you're calling the semicircle representation, and that's the Fermi surface. Okay? So it's like if you have a potential like this, something like this, okay. Maybe this is bad because there is tunneling. You sort of feel the fermions up to this. There is a Fermi level Kf, and that's your ground state. Okay, so for example, you want this that would correspond to some wave functional. And in that case, this will be the entanglement in the ground state. If you want some excited state, take some few fermions over there, that will be an excited state entanglement. Okay, this is clear? Any questions so far? Okay. So if you calculate this thing, so let me draw the line here. Call it delta x. Nowadays there are many modern ways of calculating this thing. Condensed matter people have figured out how to do these calculations with the density matrix. It basically turns out that you can write the answer in terms of cumulants of the number operator in that region. So it sort of basically reduces to some calculations of expectation values. So let me tell you the answer. So, yeah. This is base space entanglement in the second quantized theory. Yes, absolutely. That's what I'm trying to say. This is based. Why is it target space? That's it. I'll not show that this is the same as a target space entanglement in the first quantized formulation of the theory. And those are identical. Yeah.
So in the large end limit, there's some target space picture for that matrix model.
But let me come. Let me not talk about it. Let me just do this model. Okay. Forget about string theory, forget about bulk, forget about everything. System of fermions in some potential. Well, if you choose the potential properly, there is a bulk interpretation. But if it is quantum Hall effect, it's quantum Hall effect. Okay, so that let me concentrate on that first. Okay. Good. Okay, so if you do this calculation, what you find is an answer for small enough delta x, and there are better answers delta x, where kf is the local Fermi momentum and mu f is the Fermi level. So we call it mu f. So this is like the velocity at the Fermi surface. Okay. So you get an answer which is this. The answer is sort of suggestive. The first thing is, there are better ways of writing these answers, going to some different coordinates, which makes it a little more transparent. But the two things interesting about this answer, the first thing, it's a log. Okay. And then this is a factor which is 1/3. Okay. Yeah.
What's x in that expression?
X. This x.
I mean, the picture with the delta x.
This is delta x.
Yeah. So x is the middle point. X is the location of the interval.
Yeah. Oh, sorry. This x. I should maybe call it x0. But there are actually better formulas when the interval is large enough. But I'm just, to emphasize the point, I'm just doing it for a small interval. So you just replace it by the center. Yeah, by the location of that. Okay. This looks very similar to a very well-known formula for an entanglement entropy of a CFT in 1+1 dimension. And that answer that the divergence of epsilon raised to the d power 1 becomes a log in this case. So it looks like an answer of a scalar field theory. Okay. But there's no epsilon. Okay. The epsilon was some UV cutoff if I do conformal field theory. But there's no place to have any divergence here. There's something which is hidden, which is actually sort of divergent, because if we calculate our kf in terms of the number of fermions, that number would appear here. Okay. But I can do it for a finite number of fermions and everything is finite. Okay. And it can't be infinite because after all, you're talking of some n particles. There's nothing in it. Okay. The fact that it is so it looks like a single species of a massless boson. The entanglement sort of reflects that fact. And of course, the fact that this is a single massless boson is very well known because small fluctuations around the Fermi surface, any Fermi surface, is going to give you a massless boson. It's basically got to do with the fact that even for free fermions, the energy is k square. And so if k is kf plus, say, q, so the energy is the ground state energy plus kf times q, and that's like a relativistic dispersion relation. So that's, of course, a characteristic feature of a Fermi surface. So we sort of understand why there has to be a log, because at the end of the day, it's sort of equivalent to some massless boson, which is moving. And we also sort of understand why this is there, because just the fact that it's a Fermi surface, and a Fermi surface is a finite kf. Okay. So there's nothing mysterious about this answer. So let me now come to the string theory meaning of that. Yeah.
If you thought of this as a fermionic field theory, the central charge would have been half of that of a boson, right?
Right.
But because non-relativistic,
But because the it's a fixed fermion number, so the excitations are pairs of fermions. So, and that's what this is reflecting. Right. This sort of starts looking a little bit puzzling if for the special case, something called a double-scaled matrix model, I'll not deal with any details of this thing. At the end of a very long day, at the end of this, it's basically fermions which are moving on an inverted oscillator potential. Okay, and the bosons, which the bosonization of these fermions gets reinterpreted as the physical dynamical degree of freedom of a two-dimensional string. Because in 2 dimensions, a string has no transverse oscillations. So there's only a translation mode of the string, and that's like a scalar. It turns out it's a massless scalar. And there have been a lot of detailed, nowadays, I mean, this agreement between this model and string theory has been sort of impressively extended to many non-perturbative effects, including d-instantons due to the work of Ashok Sen and others, and G-in. Okay. What is Kf in here? If I look at the boson, it's sometimes called the collective field. So it's basically this bosonization of that fermion field. If this was a relativistic fermion and the fermions were free, the boson would also be free. That's, of course, very well known. Okay. Chiral, fermions go to chiral boson. Okay. If the fermions are non-relativistic, there is a dispersion of energy. The group velocity is non-trivial. Because of that, what happens is that this boson is self-interacting. And when the number of fermions are large, there are cubic interaction terms which sort of roughly look like this. Some part phi plus dot dot dot. And if you ask what is appearing in front of this, it is basically 1 upon kf of x, or kf of x is defined by this. Okay. In some sense, this can be derived. Okay. So what this means is that this boson is an interacting boson, and the coupling of that boson is given by the inverse of the Fermi level. Okay. And now you can sort of understand why non-relativistic fermions would have an interacting boson, whereas relativistic do not, is because the Fermi surface in a relativistic case is replaced by the Dirac, which has an infinite depth. So basically, this Kf is infinitely large everywhere you do, and so the coupling just goes away. This object is like an effective string coupling. It's a function of this position x, because if you look at what the string theory is, and I'll not go into a detail, it is a dilaton background. It's a famous linear dilaton background. As a result of that, the coupling, the string coupling, is position dependent, inhomogeneous. So what one has found here is that, so if you write this thing, and in this particular case, there is a much more careful calculation by Hartnoll and Mazenk, which does this calculation very carefully. And so what you basically find is, for a small interval, okay, it turns out that there's a certain limit you have to do to arrive at this potential. It's called a double scaling limit. What it corresponds to is, roughly speaking, the following: start with a nice potential like this, and there is various versions of the string theory, fill both sides. And what you do is, so this is the Fermi surface, you take a limit where the Fermi surface approaches the top of that potential. Okay, so then you can see that the energy levels have become basically continuous around those points. And then you zoom onto this part, that's what this double scaling limit is. And once you zoom on it, the only thing that remains is that hump. I mean, that's what. So, and this is something which I don't completely understand. I can sort of understand that when the number of fermions is finite, everything has to be finite. But it turns out that this object is obtained when you take the limit, let me call it epsilon f, n goes to infinity, g, something called g string. Actually, I should call this g string by this. This thing held finite, so it survives in this double scaling limit, even in the limit of large number of fermions when you take that limit. And that is that quantity that appears in this formula. So the reason is sort of weird is because I started out by saying that you would expect, you might expect a result which is finite because L string is finite, but this is finite because the string coupling is finite. It's a finiteness of the string coupling which makes this thing finite. And that's not something which people would have expected. I think it has got to do with the fact in modern days, I think many people figured out, I mean, much later, I mean, including Emil here, that these fermions are some unstable d-branes of this theory. So what this is actually calculating, something which has got to do with d-brane physics. I mean, not so much in terms of the, this massless scalar physics. The relationship between them, I don't completely understand. It's something which I think needs to be understood. Okay, and d-branes are string coupling enters in any description of d-brane, so maybe that's what a reflection of this is. Okay. Very good. So maybe I take a break now and come to the next part. So the next part, what I'm going to do is, I'm not really interested in this. I'm interested in theories with many matrices. I mean, eventually I would like to do something in the BFSS theory, for example. Okay. If you have many matrices, you can fix a gauge where maybe one of the matrices is diagonal, but you can't certainly fix a gauge where all the matrices are diagonal, right? If they are not diagonal, the eigenvalue space of whatever that matrix is doesn't capture everything. So you have to deal with the fact that this basically has n square degrees of freedom. The moment you had a second matrix, the number of degrees of freedom go from n to n square. Okay? So therefore, you don't have this crutch of second quantization where, the thing was just an extension of what we did. Field theory, you got to think directly in terms of matrices. So to begin with, so what we really need to understand is that what is this thing which we computed means in terms of a first quantized picture. For non-relativistic field theories, they are completely equivalent. So if there is a description in terms of second quantized picture, there should be a description in terms of first quantized picture. Okay. So we need to figure that out. And once we figure that out, maybe that can be extended to the case of multiple matrices. Okay? Right.
In the studies theory, you can always do the computation for the interpose in entropy, and you always get a log delta S over epsilon.
Yeah.
But why does this coupling becomes epsilon?
The kind of thing which we calculated, I did not do a calculation in the bosonic theory. I did a calculation in this theory. These are n particles. There cannot be any space for any divergence.
Okay, so your bipartition space is a field in the field.
So the partition is the space on which the second quantized field is living. And in the next hour, I'll describe what does it mean in terms of those particles, those fermions. And that's the thing we are going to extend to matrices. Okay?
Is it understood in this way? Maybe near the horizon, like a near horizon limit. In this double sling limit, you're keeping a set of state, maybe a finite number of set of states, so that the epsilon, there's no UV divergence.
Actually, if you do that,
Yeah.
just take that near hump limit, you have the perturbative worth of states is exactly that of a massless boson. So that's an infinite number of states. Yeah. It's the fact that this has a finite depth that is providing a UV cutoff. I mean, you can do this, and the calculation which I did back then was not for this, but just for free fermions. The Fermi surface is like this, minus kf to plus kf. This is momentum. This is position. And you take a region like this. So this has a finite depth. In relativistic fermions, which is the same as relativistic boson, this picture is replaced by the Dirac sea, which has infinite depth. Okay? And it's a finite depth of the Fermi surface which is giving this result. It is this object, but as I said, strictly in that limit, the depth has also actually gone to infinity because of that limit epsilon going to 0, n going to infinity, and it has become an inverted thing. But you do all calculations with finite n and finite epsilon, and if you take the limit, it still turns out that the answer is finite. That part I don't completely understand. Yeah. It's sort of what is happening here in the inverted oscillator. It is like this, and you're taking an interval like this. See, effectively, you are seeing the bottom of the Fermi sea here. Okay. And of course, if you go further and further, this goes deeper and deeper. And it's a kind of the local depth which is appearing here. Okay. So in the next hour, I'll just describe how to describe it in terms of particles. And, there are applications of this just to regular condensed matter systems, because there are many condensed matter systems where we know the wave function, have good guesses for the wave function, like the Laughlin wave function for the quantum Hall effect. But a description in terms of a second quantized theory is not so easy. So it actually is useful. In fact, people have used this in the condensed matter literature. Good. Shall we take a 5-minute break? So I'll go step by step. Eventually, we want to figure out what to do with a wave function of a matrix. But that's what the aim is. But let me go step by step and continue the discussion for a single matrix. Okay. Partially gauge fixed, namely, you reduce the matrix to eigenvalues. And so, as I said, what we want to capture is what we just discussed in second quantization, but in terms of particles in the first quantized picture. And there should be a one-to-one discussion. I mean, there's no mystery here because, for example, the state with some number of particles. This is first quantized. A stands for antisymmetrization because we are dealing with fermions, is nothing but and this is the second quantized description. In the first quantized description, there is an antisymmetric wave function, which is this, which is a function of the particle coordinates. In second quantized, it's a functional of the second quantized fields which is, in some basis of eigenstates of the field operator. Too many sides here, but I hope it's sort of clear what I mean. Okay. Good. So let's try to think about how to pose this problem in terms of this wave function, of the many body wave function. Okay. So what does it mean to take an interval or a position in the space on which the particles move? That's why I'm calling it target space, because that's where, the theory in terms of first quantization is, something like, action is not important, it's some x dot square minus v of x. Okay, so it's a target space of x, which is, it's a single particle sum over all particles. Xi square. So it's a target space of this theory, which is the space on which these particles are moving. In the case of the c equal to 1, it's the space on which these d branes are sort of moving. Very good. So what turns out is the following. If I take a region A of this target space, B is the complement of, I'll just do it with a bipartite case, but you can, of course, extend it to multiple intervals. If I call the Hilbert space of n particles as the span of the antisymmetrized kets, then this Hilbert space breaks up not as a product, but as a sum. And I'll tell you, so here all the x's lie from, say, minus infinity to plus infinity. It sort of breaks up into this, where this notation stands for the following. Okay. So this is the Hilbert space of, which is responsible for, actually, let me not write n minus, it's a bit confusing. Just write it like that. A set of vectors where you have k, not n of the particles, again antisymmetrized, with the condition they all lie in that interval A. And k goes from 0 to n. Okay. The reason why it has to be this way is because given some wave function psi, right, if I integrate that wave function only over the region A with all the mod psi square, that gives a probability of anything lying in A, but I can ask what is the probability of finding k particles in A. Okay, a given wave function is some function of the coordinates, right? So I can ask what is the probability of finding k particles in A. K can be anything. There is a certain probability given some wave function of finding one particle in A or two particles in A, up to all the particles. Just to give an example, let me do the case of two particles. So for two particles, this decomposition is, this is the Hilbert space where both the particles, so this is the Hilbert space of one particle in A, quite trivial, and No particle in A. But that's of course the same as 2 particles in means 0 particles in B. And similarly, 1 particle A means another particle is in B. But of course, these are identical particles. So you can't say that this particle is in A and that particle is in B. But you can, but an invariant statement is one of the particles is in A, the other one is in B. And the sum is necessary because you have to cover the entire Hilbert space. Okay. Now, suppose in such a setup, I am interested in operators O, which act non-trivially only if on particles in A. What that means is that over here, put in some detectors here, but there are none over there. And so this detector is going to click only it finds a particle there. I mean, if there is no particle there, it doesn't do anything. Okay. Or in other words, such an operator will have the property in this example of 2 particles is, if I take this operator and write it like this, where this have the where X lies in A. So this is the example of one of the particles lying in A and the other particle lies in B. Right. So this is this A is always there, always antisymmetrized. So what this means is that this operator doesn't do anything to the particle which is living on the complement. And it does something to the particle which is living in A, and the result of that matrix element is this O of XX prime. Okay. Then of course, you can sort of extend this to all objects. And then you can ask that given some state of the system, of the entire system, it could be a mixed state, but let me just discuss just pure states of the entire system. So I have some wave function, antisymmetrized wave functions of these 2 particles. I can ask, what is the density matrix which reproduces all the answers for expectation values of this operator? Okay, that's not very hard to figure out. You can easily see that density matrix, this is a density matrix. So this is in the sector which I'll call K equal to 1 sector. So K equal to 1 sector means that one of the particles is in the A, the other particle is in the complement. This is an operator which lives in this 1 particle Hilbert space, not in the 2 particle Hilbert space. Okay. So this will be a function of X and X prime, and it's very easy to check that I called it dy, which is an integral over B. It's easy to check that the expectation values of operators like this can be obtained by taking rho this. Again, this operator is an operator in the single particle Hilbert space, and it can be reproduced by like this. And of course, you can extend this for any number of particles. So for each sector K, so let me write the general formula. For each sector K, is given by yn xi y, I don't know, k. This I runs from 1 to k. This runs from k plus 1 to n. Same y here. So that's being traced out. Okay. So this I'll call the density matrix in the sector which is labeled by K. Okay. If I want the full density matrix, that's clearly sector-wise diagonal. Namely, the full density matrix can be written like this. Sorry, rho 1, rho 2, rho n. This is the density matrix in the sector where there is one particle in A. This is the one with two particles here. This is with all particles in A. Okay? And each of these is not normalized. So rho k is not normalized. In fact, from that formula, I can calculate, let me remove the index R here. Always reduce density matrices. You can, from that formula, if I take the trace of rho k, so just for the two particles case, it's like, or in general, it's like d dyn dxn, and then psi of y k plus 1 to yn, and the psi star of the same thing now because I'm tracing over. So this object, the integrals over y are over b, the integrals over x are over a. Okay? And this is clearly just the probability to find k particles in that region, given your original wave function. Okay? So trace of rho k is a probability. I can define a normalized object, which is sometimes useful. Trace of rho k. And if I start with calculating with this density matrix, the entropy is trace rho log rho. This trace breaks up into traces of one particle, two particle, three particle things. That's a sum over rho k log rho k, and I'm now running over space. So this, I'll just write it. You can check, becomes pk log pk Actually, let me write this formula here. Let me keep this. Everybody can see the formula that I wrote it here. This entropy has two pieces to it. The first piece is a classical piece called the Shannon entropy. It just calculates for you the entropy associated with a certain probability distribution, which is given by this p case. The second part is what in the literature is called a distillable entanglement. That's really, in a sense, getting the quantum piece to it. So that object is as if this rho hat of k is not a pure state. So there's an entropy which is associated with it, right? So it is that entropy weighted by the probability. So that's what the story for a single matrix. Now, it takes a bit of a work, and that's what we showed, is that since there is a one-to-one correspondence between states, a state is a state, it's up to you how you represent it, but we know how a certain state in the second quantized theory corresponds to the state in the first quantized theory. So you can take this density matrix and you calculate its matrix elements say, in the first quantized Hilbert space, all the matrix elements, and you can show that that is exactly equal to the matrix element of the density matrix in the second quantized picture. Okay. Which is not surprising because we sort of followed our nose in what we did. Very good. This is in terms of, these are particles. There's nothing to do so much with matrix models, but this just happens to be just the one matrix quantum mechanics. Okay. So as I said, and in fact we did that, we sort of applied this kind of formalism to cases where, wave functions are, many body wave functions are known, they're good guesses, like in particular the Laughlin wave function for the quantum Hall effect. But a second quantized thing is not very well known. Whereas, ways to calculate entanglement entropies are better known in the second quantized framework. Okay. So this can be useful. Let's now go back to the question, what did we actually do in terms of the matrices? Because that's what the question we want to understand. Let's get rid of this. Or in other words, we want to express this quantity in terms of a gauge invariant notion, not in this gauge. Okay. You can think of it in many different ways. I think the most useful way of thinking about it is in terms of observables. So in terms of, you have a set of observables which correspond to a certain operator in the quantum mechanics, and you take a subalgebra of those operators and you ask, given a state of the entire system, what is the density matrix which calculates expectation values of all operators which belong to that subalgebra? Okay, so that's a sort of useful way of thinking. So we want to express this in terms of those operators. And clearly saying that you are interested in some subset of operators of the full theory, you need some kind of projection of the full Hilbert space. So let's define a projection operator. I'll first do the definition and show that it's exactly what we thought about here. So define a projector. I'll still not yet gauge invariant. Let me just do a projector which carries an index I, runs from 1 to n, which I'll write like this. So what does it do? This thing tests whether x belongs to A. Then this delta function is 1, otherwise it's 0. So it's like a theta function. It's basically a theta, it's called something indicator function, which is 1 in interval, 0 outside. Given this projector, starting with some many-body operator, what are the many-body operators like? Many-body operators are like sum over I to n, some xi to the power m times xi to the power n, where p are the conjugate momentum to x. I mean, I have ordered in some particular way, but if you want to some different ordering, use the commutation relations to reduce like this. It's a many-body operator because they just sum over all the particles. This is the object which has a second quantized description minus I. This is the second quantized description of that operator, where psi is the second quantized field. Mixing of what?
I and J sector.
Yeah, so but there has to be a sum always. So always you break it up into some products of sums. Yeah. Here it is same I, but if you want, something like I, it has to be sum like xi, pj, xi, pj, pi, xj. So you always sort of write it in this form as products of these things. Okay. N.
X to the power of little m.
Oh, sorry. M. Yeah. Thank you. Good. So you can sort of easily check. For example, this is a projection operator squares to itself. Okay, because product or delta functions with an integration. Theta square is theta. Theta is the Heaviside function, if you wish. And so this does the job. Given some operator like this, you replace that operator where all the xi's are replaced by pi, pai, pai. All the pi's are replaced. Too many p's. Pi. Let's call it pi. Conjugate momentum. Doing this, starting for an operator like this, you get a new operator, and where for each x and each p, you just project it out. Okay? And just by construction, it's not very hard to see what these new operators are. They're going to be non-trivial, only acting on those particles which are lying in A. But it's going to have a trivial action if it is not in A. I mean, that's a simple exercise. You can do it for yourself. Like take, for example, a two-particle wave function, take some operator, do these projections. I mean, for example, let me just give you the result. I'll go through the steps. So if we start with, say, two particles, let me take this. This works for bosons or fermions. Just let me do it for fermion, some antisymmetric wave function, some Slater determinant. So I'll call the operator projected to OP. You can easily check that this object in the full Hilbert space, this is what you want to calculate. Just plug it in, plug everything in, and there's an explicit expression in terms of the wave functions, and then you calculate. What you find is the result is this. So for the operator, this, where the operator PO is, say, x1 square plus x2 square, or x1 n to m to the x2 to the power m. It's a little bit subtle to put in the momenta, but that works as well. Then the operator projector is P A x1 PA plus PA x2 MPA. Everything is explicit. This is written in terms of delta functions. Just plug it in that expression, and this is right claim. The result is psi plus 2 dx1 over A dx2 over B You see, there is only one term here, and there are two terms, x1 to the power, x1 to the power m and x to the power m. So this is the sector which is, I call 2. Sector k equal to 2. And this is the sector with k equal to 1. This is the sector in which one part, both the particles are in A. The integrals are not over the entire space. It's just over A. Here, there is an integral over B, but there is no non-trivial operator here. So you can, do that integral over B of psi star psi, and you precisely reproduce the density matrix. Okay. And this, of course, works for any number of particles. Very good. So that's a story with first quantization. That's the first step. But we have to think in terms of matrices. This came from a matrix model. What is it in terms of a matrix? In terms of the matrix, what you need to do is the following. So I have a single matrix, which I call M. There is an operator for the single matrix M. And you define a projection operator, which is a matrix valued object. I'll tell you what this thing actually means. So what does this mean? The right-hand side is a matrix valued object. I mean, one way of thinking about this is to write this as so that is the matrix, if you wish. Okay, so right-hand side is a matrix, left-hand side is also a matrix. So it's a matrix valued projector. The operators of the full theory are like trace. These are the invariant operators. Trace, I mean, M, I don't know, 25 M, some pi M to the power N, various orderings. Put a string of M's and strings of pi M. That's the most general operator in the theory. So you replace each M, P, A, M, P, get a new object, and each pi M by P, A, pi M, P. Stick it in. What you get with some operator O, if this is the operator O, then you get a projected operator. M factors, and then N factors. And now we have to take into account the fact that you cannot just pull all the P's out because, I mean, these are all matrices by themselves. They're operator, matrix valued operators, all of them. Okay. And you can, so this is some abstract construction. What does it mean? Of course, everything is now gauge invariant. I mean, there's a trace of something, so it's completely gauge invariant. The operators which you have constructed are also gauge invariant. They are projected operators. But it has this meaning what we are seeking in some particular gauge. In this case, this object clearly reduces to what we just talked about, that in the gauge where M is diagonal, this matrix will also be a diagonal matrix, and this completely reduce to that first quantized description which I had. You can just, it's quite trivial to check that. Okay? But once we have written in terms of the matrix, it reduces to the first quantization. Okay? So now we are ready to embark onto multiple matrices. This formula has to be thought about differently if you have multiple. What is this M? So let me suppose I have a theory of, I don't know, not that, I mean, the calculations haven't been done in what I am going to say, but it has been done in sort of more simpler situations. Let's take BFSS model, for example. There are 9 matrices, X1 to X9. So let me call Xi. I don't know, 3 matrices like mini BMN model or whatever you want to have. But you have more than 1 matrix. These are all Hermitian matrices. We take them Hermitian. Out of these Hermitian matrices, I can form a Hermitian matrix, which is a function of this. Just to give an example. This is a single Hermitian matrix. For example, let me take Xi to be just X5. That's a Hermitian matrix. Nobody prevents me from doing that. Or I can take Xi, f of Xi, that's another Hermitian matrix. Okay? Now what I can do, I can replace that M here by that F. Erase all this. Okay? M was 1 matrix. I traded that 1 matrix with a Hermitian combination of 9 matrices. My choice. Okay? What is the physics? I'll come to later. Okay? But now you can see whatever I did for a single matrix can be repeated for the case of a multiple matrix. You can take a string of operators, like the kind of operators which are interesting in this case, like traceless symmetric in this ij indices, so on. And for every x, you replace it by pxp, where p is defined here. Okay? It looks a bit funny. I mean, it looks like in a sense, a very trivial extension of what I did for a single matrix. So what does it mean? For the single matrix, the meaning became clear in a gauge where the matrix itself was diagonal. Right? In that gauge, that became just, I mean, the theory just became a theory of identical particles, in this case, fermions. Okay. For multiple matrices, of course, you cannot diagonalize all the matrices, but you can diagonalize one F. One of them you can. Any F you choose. Any function of the matrices which itself is Hermitian, I can use the UN gauge symmetry which acts on all the matrices to diagonalize this one, this particular one. For example, I can diagonalize X5, one of those matrices. In the gauge where is diagonal, and since f of xi is taken to be a Hermitian matrix, in this case, the diagonal entries are real numbers. Okay? So in that gauge, this is a diagonal matrix, because in that gauge, f is diagonal. And you can see what is this testing for? It is testing whether the eigenvalues of that function f of x lie in a certain interval. Okay? So that's a story for that particular combination of matrices. But now I can figure out what is the effect of that on any matrix in the world. I've just written down a projection operator. So you just apply the projection operator to any matrix. Okay. So the picture, and sort of motivated by string theory or matrix theory, is like this. So just it's better to give an example. So let me take the example where that function of x is x5. And I'll draw a picture. It's a kind of a auxiliary picture where and let me take that interval E to be the region y greater than 0. Y is that thing which is integrated over. Okay. So what is this going to do? It's going to take all the matrices in the world and it's going to figure out whether, f of xi is just a single matrix x5. It is going to figure out whether the eigenvalues of x5 are positive or negative. If it is positive, you stick a 1. If it is negative, goes away. Okay. So in terms of our pictures, let me draw another direction. I'll call it with small x, call it x6, and I'll call this x5. What this means is like the space of eigenvalues of the matrix x5. Okay. So in terms of this, in a gauge where x5 is diagonal, I have an x5 which looks like lambda n, and I have an x6, I mean, all the others are of course there, which are all n by n matrices. There's n square degrees of freedom. Okay. And by fiat, I mean, no physics yet. By fiat, what I'm going to do is I'm going to represent the diagonal entries of these matrices. It's not a gauge invariant concept, but the diagonal entries of these matrices as the location on a real line. Okay, so if I draw a picture like this, then this is the value of this lambda. So lambda has an index 1 to n corresponding to the n eigenvalues. So if I just, for example, a 1 by 1 matrix would have just have a lambda here, and this one I'll call, I don't know, mu, which is lambda 1. Let me just draw a line. Mu1 to mu n, and then there is mu1 2, mu1 3, and so on, mu2 1, and so on. And now we'll see where this picture is coming from. So I'm going to draw this as like the mu1. This is lambda 1. So lambda 2. That is mu2. It's like a picture. And then I'm going to draw mu1 2 as a kind of an open string which goes like this. And the mu2 1 is an open string which goes like this. Of course, now you know where the picture is. It's like the naive picture of D-branes, where if you manage to have a state, which is a very low energy state, where you think of these as representing degrees of freedom of D-branes, and the D-branes are very, very far apart, right? The open strings which join different D-branes are very massive. Then in some sense, you can regard the diagonal entries as locations of the D-branes. So that's what the picture is. And what this is doing, it's looking for, there are n D-branes, like this, and looking for only the ones which have the lambda values positive. And it doesn't care whether the values of mu are, whether it's a positive or negative. I don't care. I'll figure out what is it doing to that other matrix, X5. We figured out what does the projection does to this matrix. It just projects out those eigenvalues which are positive. Okay. But now I have to figure out what it does to this matrix. But I have the matrix projector. So you just take that and what is right? Px6p. I want to calculate what is this object. What does this matrix become? Okay. So for that, what I will do, of course, this is all working in a gauge where x5 is diagonal. Okay. So I'm going to diagonalize x5 in that gauge, and then I'll use the Weil symmetry to order those eigenvalues also. Right? And let me order those such that k of these eigenvalues are positive, and the remaining k plus 1 are negative. These are all negative, and these are all positive. Okay? It's very easy to check from the explicit formula which I gave for P that the matrix Px6p, PA, this case is this matrix. So k by k block and 0 everywhere. It just follows. I mean, you just take that formula, go to the gauge where that projector matrix is diagonal, and just act it by conjugation on the x6. This is what you get. This is a picture in this gauge. This is not a gauge invariant picture, but the construction is completely gauge invariant. I have written everything in terms of gauge invariant operators. It's a construction which in this particular gauge looks like exactly what we are trying to guess at. We are going to take some subset of those matrices and integrate out the rest. That's what this is doing. Furthermore, this is not the only projector you can think of. This is the simple case where x5 is diagonal. So what does it mean to talk about when f of x, I'm almost out of time, when f of x is, so suppose the theory is just two matrices, x5 and x6, and I take f of xi to be x5 square plus x6 square. Then, don't attach any physics to this picture yet, right? So in terms of those pictures, what you will do is say -1. That's our Hermitian matrix. Okay. So what it does, it takes a circle of radius 1. It looks for all the eigenvalues of lambda, eigenvalues lambda of x pi which lies in this region and kicks out the rest. These are all kicked out. Okay. But this construction also kicks out these open strings. Because those are the off-diagonal blocks which, join, those points with the points inside. It turns out there is another projector you can define which also keeps those blocks. And this is the third projector which you can define, which sort of does it a little more symmetrically, keeps one of the off-diagonal blocks and not the other one. Okay, and these are all different notions of what sort of people call matrix entanglement. Okay. What does this mean? As I said, in a theory of these multiple matrices like the BFSS model, found some generic state. For example, as we were discussing yesterday, I think the n d0 brane bound state is a huge thing of n to the 1/3. All the off-diagonal, matrices sort of participate in a very big way, and there is no natural separation of the eigenvalues. But in states where, and it's in that picture, we sort of think of the eigenvalues representing locations of the D0 branes, and the off-diagonal things as open strings which join the D0 branes. Okay. In such a state, this looks at the target space on which these D0 branes are moving. The fact is that each such matrix has a natural analog of a function of a 9-dimensional space. This is just a function. Okay? And what it does, it sort of picks out a certain region on that sort of invented space and gives a notion of how much is the entanglement of that region with the rest. But in this very specific sense, namely in terms of this, in terms of these particles and the open strings. Okay. In general, we don't have a geometric interpretation like this. So this is sort of precisely what we were trying to look for. We're trying to look for something which is there, I mean, in the matrix quantum mechanics of a well-defined object, whatever that means. And in certain situations, it sort of reduces to have some kind of geometric picture where you can think of, the eigenvalues as locations of D branes. I mean, you wouldn't expect to have a definition where, there is always a geometric picture, because this is supposed to be a theory of gravity at the end. And, magically there is diffeomorphism invariance. It's going to, nobody completely understands how that happens, but it's supposed to be happening. You shouldn't be able to define something in some diffeo invariant way. But from the point of view of the matrix model, it's ordinary quantum mechanics. It's just quantum mechanics of matrices. And you could just think of the Hilbert space of that theory and define something very proper. Okay. So I'm running out of time, but conceptually it's sort of nice and beautiful. It's very hard to do a calculation on this. There are very few cases calculations have been done. And I'll give you just one example of a rather interesting calculation by Frenkel and Hartnoll. So what they did is not this holographic interpretation. But as we know, theories of matrices are sometimes descriptions of non-commutative geometries, like infinite dimensional matrices are like operators, and naturally give rise to non-commutative geometries. And one of the interesting non-commutative geometries which you can get is a fuzzy sphere. So if you have a theory of 3 matrices, x1, x2, x3, there is a very special state of these 3 matrices where they obey some x3. Maybe a factor of 2 or whatever, the angular momentum algebra, the SU2 angular momentum algebra. And so mu is basically some kind of radius, because if you calculate x2 square plus x3 square in this state, this is a kind of a semi-classical state. It's a classical configuration. It's what? Nu square minus 1 n square by 4, some formula like this. Sort of gives you a notion of a radius of this thing. So the target space in such a state is sort of roughly a sphere, but it's not really a sphere. It's a non-commutative object. It's a fuzzy sphere. And this is what the definition is. And you might ask, is there a notion of taking a region of this fuzzy sphere and think of entanglement of that region with the rest? People have thought about it for many, many, many years. So what they did is, because of this correspondence, I mean, the way we talk about this in string theory is that you actually form a brain. I mean, use the matrices to form a brain. This is how brains are constructed in the BFSS model, for example. Okay. And so it's what you are asking is a kind of an entanglement in the on the brain itself, in this case, not entanglement of some region in M theory, but on the brain itself. So they were able to calculate using quite general properties, the construction which I just described. So in roughly speaking, this is like x3, x2, and x1. And you want to calculate the thing of a cap like this. Okay. Now, because of the commutation relation and this Casimir relationship, you can describe this cap as saying x3 being greater than, I don't know, some value E, let's say. This value A is this length, which is related to this angle, somehow, which describes the cap, right? And the x3 is greater than A sort of represents like this cap of that fuzzy sphere. Okay. And so you do the thing, namely you go to a gauge where x3 is diagonal. Then you figure out what happens to x1 and x2, because those are now still in square degrees of freedom. And I'll just tell you what the answer they got. The answer they got is, roughly speaking, so basically, as I said, this kind of constraint, namely putting in that projector, is equivalent to taking for the x1 and the x2 matrices some m by m block of that. Okay, so the x1 projected is like this, x2 projected is again like that, 0, 0, 0, and x3 is diagonal, so x3 is like just these diagonal elements whose magnitude is bigger than A. And it turns out they were able to do a calculation of this quantity of trace rho log rho, because there's a further story here, because there is a Gauss law. So what happens, the Gauss law involves these degrees of freedom and those degrees of freedom and that degrees of freedom, and that the entire sum has to be non-zero. So what this is familiar in gauge theories, when people discuss entanglement in gauge theories, that the Gauss law sort of entangles in a way the degrees of freedom outside and inside the interval, in this case outside and inside the block. And there's an argument why that gives the dominant contribution. And what they find is a result which is proportional to the perimeter, which is the circumference of this circle, which defines the cap. I'll call it A, but it's really a perimeter. Okay, and the scale that appears is something which I call GM. I forgot what its relationship. This is the coupling of the non-commutative gauge theory which lives on the fuzzy sphere. So this, because they were very excited, it looks pretty much like Bekenstein-Hawking formula, except that there's no gravity here. But it has the feature that the scale is a finite object. The scale of this is set by a coupling constant. It's not just some, the scale, not just the scale of non-commutivity. The scale of non-commutivity is there, but it appears, organize itself in terms of a coupling constant. So I thought that's actually quite nice. Okay, I think I'll probably end. Okay, yes. Yeah. Yeah.
So in a model I'm going to talk about tomorrow, exactly something like that happened, and in which you can actually do the interior and exterior. I think you can do that. I haven't done, of course. I just
Oh,
learned
beautiful.
from
I'd
this.
love to hear that.
Yeah, because
Okay, yeah.
what we're doing is three matrices, fuzzy sphere.
Right,
But
okay.
In the model which I propose is something like that, but it's emerged as a solution, in which then you can have a block with off-diagonal block. So
Okay.
you have a block which is a black hole, like a fuzzy sphere block, an environmental block, and the off-diagonal one with like the open string you talk about.
Yeah.
Then you can impose a constraint which is a fuzzy sphere radius, and then on top of interior, exterior, exactly the Gauss law mediated by the link. Everything happens.
Okay,
I think
okay. Very nice.
There's a very nice chart. Also, of course, there's a fuzzy sphere gauge theory coupling constant. It's already there. I mean,
Okay.
I have all this work out already. Just this part I haven't done.
Right, okay.
So
Of course, this GM is related to nu and you know,
related
it's
to
a derived
some-
thing.
Yeah, some Planck constant.
Yeah,
and,
yeah.
and rank and
There's no Planck constant here, but just
LP. Yeah, I have a mass scale.
there's
defined
there's
by-
some.
Yeah, just a one scale.
Yeah.
So
Okay, that's very interesting. Okay. I should find out what has this all got to do with black holes. I have no idea, but you know, people talk in a very cavalier way of saying that you know a black hole is a bunch of D0 brains which are localized here, and another D0 brain which is feeling all that. Maybe in some particular very low energy states, this is true. But again, you know, one has to remember the fact that the size of the black hole is n to the 1/3. It's big. So I think it might cloud interpretations. I've just been conservative. I think, you know. Okay, thank you. You had a question.
Quick question. Do we already have some known results about the Yapon exponent in such a matrix model with the intention term?
Known result for what?
Yapon exponent. And then know what is the target space gravity theory's implication.
Well, as I said, if you just pick some arbitrary state, I don't think there is a very clean interpretation. But there could be very low energy states of the theory with very far separated D0 brains where there could be a geometric interpretation.
Yes, I
Okay.
also expect so, but
Yeah.
any person already did it and understand something.
Yeah, but I don't know whether one can have a calculation just... You're asking as well as a calculation from the gravity side.
Yeah, because
yeah.
I just think that you have a target space interpretation, so maybe saturation bound can tell us something. Or we do not have a
Yeah,
saturation
I think
bound.
for those states it does say something.
Yeah.
Yeah.
Okay. But so far,
I
no-
should also say that Albioni Lawrence and collaborators did sort of interesting Born-Oppenheimer approximation calculation for 2 and 3 matrices. And you know, the smoking gun here is that do you find an n square in that entropy? And they did find an n square. So I think I'm not that familiar with all the details of the calculation. So it reflects the fact the moment you go from one matrix to, you know, 2 matrices, 3 matrices, there are always this n square degrees of freedom. And if there is a holographic interpretation in terms of gravity, n square is 1 upon Newton constant. So I think says something. And I don't know what it says. They found n square. Yeah. In some approximation. We just guessed that it should be n square. In some. The other thing I wanted to emphasize is that, you know, just by our construction, it doesn't make sense of doing a block like this. There is a sum over M. There's a sum over sectors. You know, that's what the thing which makes it gauge invariant. It's also the make the thing that for a pure state, the entropy for an interval is the same as the entropy for a complement because it's sum over all sectors. Because otherwise it's a bit funny because, you know, the complement of this is not that, but the whole thing. But it so turns out that when you sum over sectors, you restore that property. So I think most of the work haven't done that sum really, but I think that sum is somehow crucial in this thing. There's no way you can do this without the sum is something which you don't postulate. It just came out of a calculation. The fact that you have to sum over sectors. Okay, thank you.